Does Edge AI sound like a buzzword to you?
Sometimes it definitely does, and it's been more and more popular, and especially we see it a lot when we talk about network cameras, where people want to do all kinds of different AI in their cameras, sometimes without really knowing what AI is or what it is about. So yeah, that's why we have this panel discussion today, to discuss a little bit about AI in the cameras, and how it can be used, and when it should be used and when it shouldn't be used. So lately we have seen more and more companies moving their intelligence from on-prem servers to the two different directions, either up into the cloud or down into the camera. And that's when we will get Edge AI in the camera or Cloud AI in the cloud. So that's a big transformation we have seen recently, and generally the whole AI field has really been exploding the last few years, with a lot of things going on, and especially in the products we have seen a lot of adoption of AI that have before been more nerdy tech talk, but now it's actually a lot of product owners that want it in their products because they have seen other products successfully implementing AI in applications or in cameras. So yeah, I think there's a lot to talk about here about is it a buzzword or is it not a buzzword? But generally, my feeling is that in the camera industry, in the video surveillance industry, people are generally quite aware of artificial intelligence and algorithms because they have been using video analytics for decades. But in the more traditional ways, where you have statistical models that do statistical analysis of the pixels, and you will just estimate the difference from the normal expected background to whatever you see in the image right now. And everything that doesn't fit your model is seen as foreground, so something that is moving. Which means that if you have a tree standing and swaying, then that will constantly be detected as movement and trigger an alert. So that's where deep learning is a bit different, isn't it?
Yes, definitely. So like if we summarize this, like intelligence in the camera can be considered as the ability of the cameras to perceive and understand their surroundings and act on that based on some logic implemented by a development team. While on the other hand, artificial intelligence is an attempt to mimic human intelligence by enabling like some sort of system to automate its decision making using different kind of algorithms called machine learning algorithms. One subfield of that is the deep learning field, which is a category of algorithms that's trying to mimic the human brain, so it works like that. And one subfield of deep learning is computer vision, and that's where Edge AI on network cameras comes in. And it has been here for a while, and it's here to stay.
Yeah, exactly. So you say intelligent cameras, and I'm thinking again back to this change where we changed from on-prem servers, where we had a lot of intelligence in one central cluster, and all the cameras were just dumb devices streaming video to that server, and then all the intelligence was in that device. And now we have got rid of that one, moved some parts to the cloud and some parts to the edge. And then we of course introduce much bigger latency between the camera and the cloud, where the processing could be done, but also robustness issues that if you lose internet connectivity, then your camera can't do anything, it's not intelligent. So that is one of the reasons, I guess, that we need more intelligent cameras today.
Definitely, yes. Like also cost-wise, it's very efficient to have more intelligence, I don't know, in the camera rather than in the cloud.
Yeah, exactly. You already paid for the hardware for the camera, so you can
why not use it,
just
right?
as well use it, yeah,
Yep.
Instead of paying expensive cloud bills. I think a lot of us know that AWS bills can be expensive.
Yep.
Okay, So you say that artificial intelligence is trying to represent how we think in our brain and try to do the same. And with computer vision specifically, can the cameras do everything that we can do, or how do you group the different things that you can do in computer vision?
I would say like it can do most of what we can do with our own eyes, and sometimes maybe even more. So like there are different types of computer vision algorithms out there. Like there are types of algorithms that are just tasked to detect on if this is a mobile phone or not. There are other algorithms that are tasked to find all the pixels that refer to this mobile phone. These are called segmentation algorithms. And there, of course, there are the popular and most widely used on production level computer vision solutions called the object detection algorithms, which is a family of algorithms that's tasked to both predict like the type of an object but also its position.
Yeah, exactly. So the first one would be classification, where you just classify what kind of object is this. The second one you said was segmentation. So we create a segmentation mask around the object so we can see exactly what pixels belongs to this object compared to that object. So for example, what pixels are the table and what pixels are the camera. And the last one was object detection. So position and classification combined. So typical in form of bounding boxes. So you get a square around the object.
Yep, that's true.
And there you have some differences to like pose estimation, for example, which I would guess is a kind of object detection.
Yeah, just with some extra steps there. So instead of like measuring the position in box format of an object, like we get we pinpoint different points, let's say, of human anatomy, like the hands or the face or the feet, in order to localize them and make some sort of logic around that.
Yeah, exactly. Yeah, so it's the bounding boxes is one special condition where you have two different points defined in the corners of the bounding box. And in pose estimation, you would, for example, have 16 different points, or exactly, depending on what kind of person or animal we want to detect. Or if we want to detect hands, for example, we could detect all the fingers as the joints in the fingers and see exactly how we're moving. Interesting.
And there is a lot of interest in that in the sports industry, from what I've seen, like to measure the athlete's form or like performance.
Yeah, exactly.
Yep.
Yeah, so you could get automated feedback, for example, do you have the correct shape when you are lifting this rod and so forth.
I think it's even going to be introduced in competitions sometime soon.
Okay.
Like to measure how well the athletes did, actually.
Yeah, exactly.
Rather than just having a judge, so judges be careful out there.
Yeah. Yeah, so that takes us into one interesting area where, again, intelligence in the camera, what effect does it actually have on the business? So it might be that you might have intelligent cameras that are helping people that are using the cameras. So for example, if you have an operator monitor a video stream, he doesn't need to constantly sit and watch every second of it. Instead, he can get an alarm trigger when something happens. Or it might be that he's interested to investigate a particular event. So you want to find all the moments in the video where a particular looking car went by, for example. So that would be an example of augmenting AI in the camera. And then the other one would be automation, where, as you say, you replace the judge with an AI instead and automate the whole process. And I think there's a lot of interest in the manufacturing industry, for example, to automate different kinds of processes, but also to trigger alarms. So what limitations does bounding boxes have compared to other things?
Well, when it comes to like the algorithm itself, like as I said, the object detection task can be split into two separate tasks, subtasks. So localization and classification. So that's where the complexity happens, because typically we require much more post-processing to get some reasonable results from our model and parse all the intermediate outputs of the steps. So combining the output from the classification head and the localization head. And then there is also the extra complexity, the algorithm-specific extra complexity, for example, when using anchor boxes, which is a way to encode the ground truth when training the model. And subsequently, when interpreting the predictions from the model, we need some sort of decoding mechanism, which there's no standardized way to do that for every object detector out there between the different frameworks, and that would require us to create some custom logic using some deep learning framework, which can get tricky to move into the edge, as we will discuss soon.
Yeah, exactly. Yeah, so you say classification head and detection head, or what did you call it? Localization head. Yeah. So the classification head tells you for each object what kind of object is this, and the localization head tells you where in the image is it.
Yes.
And there's been a few different generations of different architectures for these kind of models throughout the last few years with, as you said, with the
anchor boxes.
Anchor boxes, yeah exactly. And I guess another method would be the vision transformers that we see nowadays.
Yes, that's still relatively new, and we also have the heat map-based models, like a more traditional way of doing it.
Yeah, exactly. The object points, papers, and things like that.
Yep, there we get rid of some of the complexity, but there is also the performance trade-off we get from those, as they typically don't tend to be as accurate as their anchor boxes based counterparts. Yes, the vision transformer, as you mentioned, it's relatively new, and just as all the generative AI groundbreaks out there, it also is coming to take over the computer vision field. And I would say it's much similar to the object detector counterparts, minus the anchor boxes part. The main downside with it, though, is that it's very computationally expensive, and for its camera or AI accelerator we use it with, we would need to implement some very strong optimization to make it efficient.
Yeah, exactly. Yeah, so there are different accuracies that you can get from the different models, but I guess one thing is also the maturity of the implementations. That since there are constantly being new innovations in this area, even if you in a paper can get higher accuracy with a new model, it's not necessarily the best one to use for projects, because in reality maybe you can get better performance out of an older model since there are better implementations for the infrastructure. So for example, we have the different Axis cameras here, and I would say a few different generations of them. So starting a few years back, we have this one, the 1065, which doesn't have any deep learning capability at all. It's an 32-bit umbrella chip, so quite limited in computational power, and no real methods to do deep learning at all, actually. But yeah, with that said, you could of course still run deep learning models, but they will run on the CPU. So what is the effect of running them on the CPU?
So typically we never want to do that, because it would be quite slow and of course not efficient at all for a production ready solution, as we're typically interested in lightning fast analytics, especially on its devices. That's why we have these AI accelerators specialized for edge devices called deep learning processing units, or DLPUs in short. And then we have the next generation of Axis cameras here, which contain three different kinds of DLPUs as of now. So those are the RPK8 chips, which are contained in this camera, for example, and those are proprietary to Axis. So they're the ones developing the chips, and then we have, of course, the CV25 cameras, which can run deep learning models using the Umbrella CVflow runtime. And then we also have the RPK7 cameras, which can contain the HTPU Google Coral board, which is a very well supported chip for running the deep learning models.
Yeah, exactly. So looking at the release date, I guess we have this one a lot earlier than the other ones. And then we got this Umbrella camera, or at least if we look on the dates of the chipset in them. And then we have the RPK7 with HTPU, and we have the RPK8. And hopefully soon we will see the RPK9, which will have another DLPU version. But does these release dates always mean that the newer cameras are faster when you run models, or better?
Well, typically yes and no at the same time. So, for example, the RPK8 chip usually competing with the TPU. On theory, it's a faster machine and a better performing one, but it also has a lot of limitations compared to the TPU. While, for example, the TPU, while technically on paper slower than the RPK8 camera, has a much larger track record, I would say. So there is very good documentation on it online, and a wide collection of models that are known to be able to run, and that can be easily trained and customized to work with this chip. While on the RPK8 one, which currently is optimized to support models that are quantized only in a specific way, and by quantization I mean the necessary pre-processing we need to apply to a deep learning model before we move it to the edge. So therefore representing its own internal parameters and weights in a less computationally expensive way. And we will get back to what options are available there.
Yeah.
Also all of these cameras require a lot of different extra steps in order for the models to be successfully used with them. So, for example, the Google Coral board camera has its own compiler, which needs to be run on top of the deep learning model. While, for example, the CV25 camera with the Umbrella chip has another type of compiler that needs to be used before we are able to use the model, that can get a bit tricky to use because there's not much information online on how to do this, as the documentation is specific to I think clients of Umbrella.
Yeah, exactly.
Okay.
Yeah, so we have different proprietary formats essentially. So we have the Umbrella, which has their own proprietary format. We have the HTPU based, which is using the Google's
Coral board.
Yeah, exactly. Yeah. Where the binary format of the operation itself is proprietary, but it's still using the open source TensorFlow runtime or TensorFlow Lite runtime.
Yes.
So it's a little bit more open than the Umbrella ones. And then we have the RPK8 one, where everything is hidden in the camera. So you load it with an open source TF Lite model, and then internally it handles it to map it to the hardware. But yeah, we can also say that essentially what you say are that they are optimized for different things, and they have their own weaknesses and strengths, which means that different models will be running differently quickly in the different cameras. So it's not obvious that a specific model will always be fastest in the RPK8 one, since that's the latest one. It could be another one of the cameras that is faster.
Or more accurate.
Yeah, exactly.
Also, yeah.
So that probably means that if you want to support a lot of cameras, optimally you want to run different models in the different cameras, because you want to use the one that is best suited for that particular hardware in that camera.
That's correct on that one. So that creates some complexity, I guess, for the client that wants to use the models. So do we always need to make different models for all the cameras?
Yeah, exactly. That's a good question that I think many people want answers on, and I guess it's not that easy to answer. So yeah, I'm thinking about two different use cases. You have the greenfield projects, where it's a new project you want to do, particular for the Axis cameras. So it might be that you're creating a new type of product that you want to sell, and you are only targeting this product on the Axis cameras. And maybe you can even say that in all our installations we will use the P3265 camera with the ARPA-8 chip, which means that you just need to have one model. While if you're selling the ACAP as a product, and people themselves can buy the cameras and install them, then maybe you want to support all of the Axis cameras, which will give you a lot of different DLPUs that you need to cater for. Or maybe you already have a product in the cloud and you want to have an alternative implementation in the camera. So you want to run the deep learning models in the cameras that does actually have a DLPU, but you have also older cameras in your system that doesn't have a DLPU, and then you want to run the inference in the cloud instead. So you end up with a lot of different models then, I guess. Is it possible to create one ACAP that can do all of this?
The more cameras we want to support, the more let's say compromisations we might have to make when it comes to model performance, or we need to decide the trade-off between inference speed and accuracy sometimes. So we end up in some threshold that's acceptable for our use case.
Yeah, exactly. Yeah, so we can essentially train one model, which will then be in-date quantized to work in the cameras, and the same model will run in both the edge TPU and the ARPA-8 camera, for example. And we can even run that 8-bit model on host or in the cloud if we want to. So it is possible to run the same model. But considering the compilation step, we probably still need two different applications for those two cameras, for example, to have one model compiled for the edge TPU and one model compiled or not compiled for the ARPA-8. If we have the two different models, we need one compiled model and one TF-Lite model. So if we have two cameras with different DLPUs, we probably want to build one EEP file for one camera that contains the compiled TF-Lite model, one EEP file for the other camera that contains the original TF-Lite model. But yeah, then of course we could take both of them, bake into one EEP file, and select which one.
But then runtime.
Yeah, exactly. Then we end up with an EEP file that is twice the size that it needs to be. So then we might have limitations due to that instead. So it's essentially a zero-sum game. You always have you need to select where do I want to put the effort. Do I want high accuracy? Do I want high frame rate? Do I want a small EEP file? Do I want a portable EEP file that can go in many cameras? Can I accept having an SD card in the camera, and so forth?
Yep, a lot of different options and considerations to make out there when running deep learning applications on the Axis devices.
Yeah, exactly.
Maybe we should lay a word also on the actual differences on running the models in the two cameras, for example, the quantization type. As of now, the ARPA chips, the latest one being the ARPA-8, can support models that are per tensor quantized. So quantization parameters are a parameter that helps us represent the internal parameters of the model in a low precision format. That means that for the RPEC 8 chips, we only get one parameter per tensor of the model. And even though we can run models that are per channel quantized on the RPEC 8, it will be far less optimal, and that means we will have much higher inference times, so maybe even 10 times slower than their RPEC, than their per tensor counterparts. That is not a limitation for the TPU, as it can both support models that are quantized per tensor or per channel, even though we have seen that sometimes the per tensor quantized model are also less accurate on the TPU.
Yeah, exactly. Yeah, so this is one of the points where it gets quite confusing, because we have the RPEC 8, which is newer than the TPU cameras, and we have per channel quantization, which is newer than per tensor quantization. But despite that, it's the newer camera only supporting the older quantization method, and the older camera supporting both the new and the old one. So yeah, in the newer cameras we can run both per tensor and per channel, but per tensor would be very slow.
Per channel.
Per channel would be very slow, so we shouldn't use that. And in the other one, it supports both of the quantizations, but we still probably don't want to do per tensor quantization if we can avoid it.
Yep, that's true. And then of course we have the umbrella chip that is a bit more flexible when it comes to what type of models we can run on it, meaning coming from different frameworks. As we mentioned that the HTPU camera and the RPEC 8 typically support models that are in a TF-Lite format, TensorFlow Lite format, while the umbrella chip can also support models that were created using PyTorch and converted to ONNX, another format for representing deep learning models, and that gives us a bit more flexibility in that part, as a lot of implementations and a lot of companies typically tend to prefer PyTorch for their research and development of models. But that doesn't necessarily mean that we can't make use of implementations of models that were in PyTorch for the other two cameras. There are some unofficial though solutions of converting models between these two frameworks, the TensorFlow framework and the PyTorch framework.
Yeah, so I think this is a good segue into the talk of the different frameworks. But taking a step back, we have been talking a lot of details about the particular hardware that is in these different cameras and what models they support. But when you develop a model for your own computer with an NVIDIA GPU or a cloud computer, then you typically don't need to think about all these kind of things, what particular kind of accelerator there is in your GPU. Why is that?
Yes, for example, the TensorFlow Lite format compared to the TensorFlow native counterpart, has I don't know, is it 1/10 or something of the supported operations that TensorFlow has?
Yeah, I think
it supports a much smaller range of operators. It can also get quite tricky to represent custom layers of a model if we have some custom implementation of, for example, for object detection parts, the encoding or decoding or post-processing of the detections and the inputs. And what else is there? Also typically some operations get quite bad accuracy when they're quantized, so we also need to account for that.
Yeah, exactly. So you could almost say that GPU in this case could stand for General Processing Unit, where general tends to be everything that is parallel. So yeah, looking on your computer, you have your CPU, which does sequential execution, GPU that does parallel execution. So essentially, as long as you can phrase your mathematical problem or your deep learning model as a parallel computation problem, then you can calculate in the GPU. But these cameras, even though some of them has a GPU, that GPU is not made for deep learning, and that's not what is being used when we run the deep learning models. But instead it's the DLPU, which is a very specific chip with, as you said, just a few set of operations that are common in machine learning or deep learning that they have implemented hardware acceleration for. So we're very bounded to what particular operations are implemented in a particular camera and which format they need to be. So it's that process of converting between different formats that can be a little bit tricky. For example, if you have a PyTorch model, as you were talking about, and you want to run it here, where the runtime in these two cameras is a TF-Lite runtime. So then you need to somehow get your model from PyTorch to TF-Lite runtime to be able to run it in the camera, which you wouldn't need to do if you run it in your computer.
Yep, that's true. As you said, like we would need to have some sort of converting the model between frameworks, which always adds extra complexity to the problem. And sometimes it might not even be possible at all. So you would need to remake the model in TensorFlow, which can be quite catastrophic, I guess, as it could be a different implementation.
So in summary, we can say that it is possible to write a model in another format, but you need to convert it sooner or later, and that can be a hard part. So yet again, if you have a greenfield project, then you have the opportunity to write your model directly in the TensorFlow format, which might make it easier.
Yep, and it's also, of course, the quantization options that we talked about earlier that are different between frameworks. So, for example, if you decide to do that and develop your model using PyTorch, and it's per channel quantized, and then you decide that maybe I need to change that, it can get very tricky or almost impossible sometimes to go on with the same model without having to move back to TensorFlow eventually.
Yeah, exactly. So order matters essentially. If you have a model that you have that you're going to convert from PyTorch to TensorFlow, and if you're going to do quantization, then you need to first convert it to TensorFlow and then quantize it in TensorFlow. It's not always possible to quantize it in PyTorch while you do the training, for example, and then convert the quantized model. So yeah, that can put some limitations on what is possible. And how is it with these different kinds of models that we talked about earlier, with classification models, segmentation models, bounding box based models? Are there any difference there in which one are easy to convert from one framework to another?
I would say typically the backbone networks or the networks that are used for feature extraction from an image are quite easy to convert, as they usually involve a very small set of operators that is supported on pretty much every camera. So it's quite easy to convert those. The same thing for the classification models, because they're just contain like some a few layers of extra complexity on top of the feature extraction network. For the segmentation models, the challenge typically is that they can get quite large tensors, especially near the output. So you need to find like a sweet spot, I would say, between good accuracy, so having a tensor large enough to represent your problem, and but also that is also able to fit in the different runtimes or supported by the accelerators of the cameras.
Yeah. So there we come into another limitation. Before we talked about the different operations that we had. Probably have something like 100 support operations in a camera and thousands of operations in TensorFlow, for example. But the segmentation models are typically quite simple in terms of operations they use.
And architecture, yeah.
Yeah, but instead they have big tensors, and large tensors are not always supported in the runtime in the cameras.
That's true, yeah. And then of course you have object detectors, which, as we said in the beginning, like can have a lot of extra steps, either between like combining the localization, the classification, head predictions, or encoding, decoding inputs and outputs and post-processing them, which if they're implemented in a customized way, there is no easy way of making that compatible with the TensorFlow Lite runtime, and it can get quite tricky. Even though, like, good thing about TensorFlow Lite is that it's very well documented, and there are a lot of great frameworks out there for basically feeding your data to a training pipeline that's already tested and well known to work, and getting to your model in the right format to run on the cameras.
Yeah, so it's much easier if you go with something that already has an implementation essentially, and just throw your own data on it and get your own model.
Like the TensorFlow Object Detection API, which now has support for TensorFlow 2 also. And that means that we're not limited to some old TensorFlow 1 implementations. Or the famous YOLO architecture by Ultralytics, which is a great framework for training a YOLO model end-to-end in an end-to-end fashion, and having something that can run on the cameras with some modifications.
Yeah, exactly. So if a customer have a model that they have already trained, can they just send it to us and we make it run in all these cameras?
Well, I would say that's very optimistic to ask. So short answer is no. But yeah, when thinking about this, we need to do it in a more structured way. So typically our suggestion is like to first get the minimum viable product running on the camera. So that means like trying something that's already known to work in the camera from the different frameworks that are known to be supported and produce good models compatible with the cameras before you start training it in your own data. And so that will save you a lot of time and possibly unwanted costs or unnecessary cost. Yeah, so I would say it's pretty much impossible to just get a model and have an application running in the camera immediately.
Yeah, exactly. So part of the reason for that is that if a model is already trained and we just get the weights for the model, then there is no opportunity to change the model in any way. So if a single thing doesn't work with the camera, then it's impossible to get the model running. While that is much easier if we work with model on an architectural level where it's implemented, then we can easily change tiny things in the model that probably doesn't affect the accuracy much of the model. And then we just retrain it when the architecture is working. So the steps would be to first try the architecture that you want to use, verify that you can actually get that architecture running in the camera, and then after that you can benchmark that architecture, train it with your own data, see is it good enough, will this architecture be solving our problem, or do we need to go on and look for another architecture and make that one work in the camera. And then the first step after that would be to create automated pipelines, because we have a lot of different cameras that need different kind of compilation and so forth. And also, since the models are compiled, they will not be 100% similar in their performance. So we probably want to evaluate all the different models to see the performance of each one of them.
That's quite correct.
Yeah, and we do that with automated pipelines, so we can run one script that runs one training and outputs the accuracy on all the different versions of it. So yeah, this typically works in a greenfield project where we start a new project where they can decide freely which model they want. And in that case, the right answer is probably not the latest and greatest, because even though the model on paper is best, it's not the best when it's actually running in the camera.
Or it might not even be possible at all to run it
exactly.
on the camera.
Yeah, exactly. But yeah, we usually find it useful to differentiate or to segment our deep learning projects into 4 different categories when it comes to running them in the camera. So we have the primary use case that we talk about now, where you develop a specific deep learning based application specifically for the Axis cameras. And then you have the ability to choose essentially freely what is best for this particular deployment platform. And then we have the partial framework, where you currently have something running in the cloud today, or on an on-prem server, for example, and you want to offload some of this complexity to the camera. So that could, for example, be due to data bandwidth, that if you do the first part of the network in the camera, maybe you end up with a much smaller feature vector that you can stream to the cloud instead of streaming the whole image.
That can also get tricky, because I guess you also need to have a way of verifying that that this new pipeline is actually consistent performance-wise with your cloud-based solution. So you don't end up with something that works much worse than your previous solution.
Yeah, exactly. Yeah, so you should probably see it as a new generation of your product. It will not be the same. You can't just take one model and split it into 2 parts. Maybe sometimes you can,
but expect it to work in the same way.
Yeah, exactly.
Yes, absolutely.
Yeah, no, so it's a redesign on both the encoder and the decoder, or whatever parts you have in the system.
And another trade-off you need to consider.
Yeah, exactly. Yeah. And then we have the alternative approach, where you have one model running in the cloud, and you will have an alternative solution that is running it in the camera. So it might be that you want to support both new and old cameras with your system, but you don't want to pay for the cloud bills if the cameras have a DLPU. So then you want optimally the same version of the model running in the camera, but that's probably not going to work. So what you will do then instead is to find what is the best we can do in the camera to get the same kind of result as we get from the cloud. And in some cases that might be that you have a lower performing version that is running in the cloud. So you actually give the customers the choice to either you can have this high performance solution, it has high latency, it is dependent on the cloud, and it's more expensive since we need to pay the cloud bills. Or you can have this simpler version, which does essentially the same thing, might not work in all the edge cases, but it runs totally embedded in camera. It doesn't depend on internet. It continues working even if you lose internet connectivity, and there is no cloud bill to pay, no infrastructure in the cloud. And then we have the replacing of an old model. So
solution,
yeah, exactly, same use case, but you say that the one we can run in the camera is as good as we need it to be, so we don't need the one in the cloud anymore, and we don't have any old cameras without DLPUs. If we have that, we rip them out and install new cameras with DLPUs, because it might be cheaper to do that than to have 2 different implementations that you should maintain. So yeah, when it comes to deep learning project, you need to think structured about what do you want to achieve, what situation are you in now. So don't get stuck in thinking that we should do like this. Take one step back and think about what you actually want to achieve, and then we can discuss the best possible options to go on from there. Yeah, so if someone wants to do this project, then I guess they just reach out to us and we will help them through the journey so they don't need to understand all the complex details we talked about the different DLPUs and so forth.
Yep, I would also say that the best thing to approach is try to avoid as many of the complexities that are present, and we can help you do this like through a collaborative, iterative process of like optimizing the model.
Yep, exactly. And we offer both implementation, consultation, advice, tools. We got it all. If you want to run it in the camera, we are here to help you.